Here we're talking about oxidation and reduction reactions. We actually did this lab earlier. We combusted magnesium ribbon in oxygen, and this produced magnesium oxide. Now, we weren't actually able to look at this reaction because, you see, it's actually quite bright. In fact, it would burn your retinas just a little bit. And so, let's see, what was actually occurring. We had magnesium. That was magnesium metal, and so it was only pure magnesium atoms with each other. No overall charge. And we reacted those with oxygen gas, so individual oxygen molecules, O2. And when this occurred, you'll see that we actually turned magnesium into a magnesium ion with a charge of +2. Now, in order to turn magnesium into a magnesium ion, which allows it to therefore stick to an oxygen ion, electrons have to be transferred. So you'll see that magnesium went from Mg to 2+. It must have had a transfer of electrons. And similarly, oxygen went from being a regular old molecule to being an oxygen ion, oxide. And so it also must have involved the transfer of electrons as well. In fact, what we had here was magnesium turning into Mg2+. In order to turn into 2+, in order to have more protons than electrons, you need to lose electrons. Now, electrons are released from magnesium, and how many do you think would be released if you have two magnesiums turning from Mg0 to Mg2+? Well, there's an overall number of 4 electrons released. One way to figure this is to say there must be the same overall charge on both sides of an equation. And so if the overall charge here is 2 times 0, or 0, and the overall charge here is 2 times 2+, or 4+, then you also will need, in order to get 0 on the entire side here, 4-. So take a look at oxygen. It's going from oxygen 0 to oxygen 2-. In order to become negatively charged, in order to have more electrons than the protons that you originally had, you need to gain electrons. How many? Well, the overall charge here is 2 times 2-, or 4-. And presently the overall charge here is 0, but we need 4- on this whole side, so we'll put 4 electrons. Both of these are half reactions, showing just things which are gaining electrons or releasing electrons individually. Now, these half reactions can actually be combined to give the overall reaction. In fact, this overall reaction, later on you'll have to be able to build it from half reactions. So we combine these two half reactions, and to do that we just add everything on the left. So for example, on the left we have those 2 magnesiums. We have that 1 oxygen, O2, and we have 4 electrons. And on the right we have 2 magnesium ions, 2 oxide ions, and 4 electrons. Please note that in order for 2 magnesiums to react with 1 oxygen, the 2 magnesiums must release 4 electrons, and the oxygen molecule must absorb 4 electrons. There must be as many electrons released as absorbed. Later on we'll practice balancing equations for the number of electrons or absorbed or released. So what you can do is say, oh, these are the combination of the 2 half reactions, and in fact we get these magnesium and oxide ions, and they actually come together and they form 2 magnesium oxides. This is the overall reaction that I presented initially after we cross out what's on both sides of the equation, the 4 electrons on both sides. All right, now we take a look at this and we see that the magnesium, it lost electrons. Electrons were released from it, and so we will call this magnesium oxidized. And this oxygen molecule, it absorbs 4 electrons to turn into oxide. We will call it reduced. reduced. Now, you'll see that the magnesium actually allowed the oxygen to be reduced. You see, the oxygen, in order to be reduced, has to absorb 4 electrons. They need to come from somewhere. The magnesium released those electrons. The magnesium, it gave the electrons which oxygen absorbed. It was an agent which allowed the other thing to be reduced. So this is a reducing agent. And oxygen, it allowed magnesium to be oxidized. That is, it absorbed those electrons that it was releasing. And so we will call it an oxidizing agent. Okay. Please note that this thing which is reduced is oxidized, and this thing which is this thing which is reduced is an oxidizing agent. They're opposites. This thing which is oxidized is a reducing agent. Opposites. Okay, so you can consider the electrons absorbed or released, but there's kind of a quicker way to know whether something is oxidized or reduced. So take a look at magnesium here. Magnesium, it went from 0 to 2+ when it released electrons. Magnesium went from 0 to +2 when it was oxidized. In fact, when you go up this number line, you are oxidized. Oxidized. And you'll see that oxygen went from 0 to 2- when it absorbed electrons, when it was reduced. To go down the number line means something is reduced. Okay? You can actually kind of make it easier to remember what is oxidized and reduced. And the term is oil rig. What is oxidized is going to lose electrons. To lose electrons will oxidize something. And something that is reduced is going to gain electrons. So oil rig. However, in bio or AP bio, you might have heard the term Leo says Gur. Now, Leo stands for losing electrons is oxidation, and Gur stands for gaining electrons is reduction. Okay? So, we were just dealing with ionic charges. However, we can often refer to things being oxidized, reduced, when there are no ionic charges. We don't have an ionic compound, but instead we might be forming a molecule. So take a look at the formation of sulfur dioxide from sulfur and oxygen. Now you'll see that sulfur is reacting with the oxygen, but you don't know what's gaining and what's losing electrons, or at least electron density. In order to understand what's gaining and losing electron density, you need to actually consider what is the Lewis structure of that molecule. Now, one of these, oxygen or sulfur, is more electronegative. That means it will take a little bit more of the electron density in the bonds towards itself. Now, if you go and take a look at the periodic table, you'll see that at the top right-hand corner of the periodic table is the highest electronegativity. So fluorine is the highest electronegativity. Now, very close to fluorine is oxygen, so that also has a very high electronegativity. Sulfur is a little bit lower. So oxygen has a higher electronegativity than sulfur, therefore, in the bond between oxygen and sulfur, the electrons being shared are going to spend a little bit more time towards the oxygen than the sulfur, so that the oxygen will become relatively negative and the sulfur will become relatively positive. Sulfur has lost a little bit of electron density and has a little bit more positive than negative charge now. Now, these don't have formal or full positive negative charges. These are partial positive and negative charges. However, we'll still refer to these things being oxidized, reduced, whether they gained electron density or not. So take a look at sulfur, or actually oxygen. It was originally having a charge of 0, and now it's a little bit relatively negative. So oxygen went from 0 to being relatively negative. And so you can say that it must have gained electrons, and therefore you would say that it was an oxidizing agent. Now, one way you can kind of consider all this, and in fact we'll use this in writing our oxidation numbers, is just consider that all the electrons being shared between the two atoms will go towards the more electronegative atom. So in fact, pretend that all the electrons went towards oxygen, and so pretend, just for sake of convenience, that it has a charge of -2. Or we'll say that its oxidation number is -2. Because it has 6 protons and now 8 electrons, it has 2 more electrons than protons. And then sulfur, now it has 4, it has, has 4 less electrons than protons. And so we'll say that its oxidation number is +4. Okay, so we'll use those oxidation numbers in determining whether these things were oxidized or reduced. So sulfur is going from 0 to oxidation number of +4. We can almost consider that, let's see, electrons must have been released from it. It's going to go up the number line, and so it was oxidized. And oxygen was reduced, therefore, because if something's oxidized, you know the other thing is reduced. If sulfur is oxidized, it's a reducing agent, and if oxygen is reduced, we know it's an oxidizing agent. And so we write these numbers here. We don't mean charge here because there are no ionic charges. We'll just pretend that it's kind of like charge. We'll call it oxidation number.